Assalamu alaikum guys. Okay, so now we are gonna look at the trends in ionization energy and electrical conductivity. We completed the melting points trend, we completed the atomic radius, the ionic radius in the previous lecture. Now let's see what's happening to the ionization energy as we go across this period. We've already done most of this, the reasons behind the ionization energies increase in our starting videos of ionization energies. So you'll have to look through the playlist for those videos, of course. Over here I'm just going to do the trend and explain the reasons and exceptions, and that's it. And then electrical conductivity. Okay, as we go from sodium to magnesium to aluminum to silicon to phosphorus to sulfur and to chlorine, meaning we are going across the period, right? And remember, I told you across the period the ionization energy, it generally increases. This is the general trend, okay? It generally increases, but there are a few exceptions, okay? For instance, from magnesium to aluminum there is an exception, there is a downfall, there is a decrease, whereas and from phosphorus to sulfur there is a decrease, and generally it is increasing, okay? So now, meaning aluminum is less than magnesium and sulfur is less than phosphorus. We've already discussed the reasons behind this in our previous lectures, okay, on ionization energy, but I'll quickly review this. Aluminum and magnesium. Now, first of all, why is this ionization energy increasing across the period? So if you are asked this question, what are the points that you must include in your answer? First of all, what's happening to the atomic radius as we go across the period? Atomic radius is decreasing, right? We've explained the reason to that in the previous video. Then if the atomic radius is decreasing, what's happening to the charge? The charge is increasing, the nuclear charge, I should rather say. So if this is happening, what's happening to the charge density? The charge density is increasing as well, because what is charge density? Remember, charge density is the charge per unit volume, meaning charge divided by radius. You could think of it that way, but it is charge per unit volume, okay? And remember, I told you that if the charge density increases, then of course the nucleus will attract the outermost shell electrons more tightly. And there is another thing as well, shielding effect. Guys, remember the shielding effect? I've explained that as well in the previous videos. What is shielding effect? It is the repulsion provided by the inner shell electrons to the outer shell electron, meaning it is the effect by which the inner shell electrons, they shield the outer shell electrons from the nuclear attraction, right? So that's the shielding effect. The shielding effect as we go across the period, it remains constant, remember, because there are no additional shells added as we go across the period, so it remains constant. If the nuclear shielding effect is constant and the nuclear charge increases gradually as we go across the period, then that means the outer shell electrons are going to be more tightly attracted to the nucleus, and hence the more energy will be needed to overcome them, to remove them from the outer shell electrons, and therefore the ionization energy has to increase generally. Now, why are there exceptions over here? Now let's explain the why to the exception. Sorry about this. Okay, now basically from magnesium to aluminum, why is aluminum having a lesser ionization energy as compared to magnesium? First of all, for this you'll actually just need to look at the electronic configurations, okay? Magnesium, proton number 12, 1s2, 2s2, 2p6, 3s2, and I guess this is 10 and 12. Okay, this is magnesium's electronic configuration, whereas for aluminum it's entirely the same, 1s2, 2s2, 2p6, 3s2, but there is a 3p1 as well, okay? Now in case of magnesium, the outer shell electron, it is on a bit outer as compared to magnesium, okay? It is, meaning it is not in the 3s. For magnesium it's in the 3s, right? For aluminum it's in the 3p, meaning it is being shielded by all of these electrons. Whereas for magnesium, it is only being shielded by these electrons before 2p, okay? So since the shielding effect is better, or it is more dominant for aluminum, therefore the outer shell electron is going to be less tightly attracted to the nucleus, and so lesser energy would be needed to remove the outer shell electron in case of magnesium. In case of sulfur and phosphorus, again you'll need the electronic configuration, but there's a slightly different reason for sulfur and phosphorus. If you look at the proton number of phosphorus and sulfur, proton number of phosphorus, where is it? Okay, here it is, 11, 12, 13, 14 and 15 and 16. Okay, this is proton number is 15 and this is 16. So now write down the electronic configurations. So for phosphorus is going to be 1s2, 2s2, 2p6, 3s2, and 3p3. Whereas in case of sulfur, it's entirely the same, but there's a difference in the last orbital. It's 3p4 over here. Now compare the 3p electrons, okay? The 3p3 electrons over here and the 3p4 electrons over here. In case of phosphorus, it's gonna be, you've got the 3 orbitals of p, right? They're all half filled. So 1, 2, and 3. But in case of sulfur, you've got 3 orbitals, and according to, if you start filling them out according to Hund's rule, you have to first fill them singly, and then the 4th electron, oops, sorry about that, then the 4th electron has to be added over here, right? 4th electron has to be added over here. This means this is sulfur and that's phosphorus. Now whenever pairing of electrons has occurred, what the pairing does is, since both the electrons, they are negatively charged, so the pairing would actually cause the electron to become less tightly attracted to the nucleus. Okay, this is called spin pair repulsion. These electrons will repel one another. This is called spin pair repulsion because electrons have become paired over here, right? So they'll become less tightly attracted to the nucleus because this electron over here is already trying to kick this electron out from its orbital, right? So therefore lesser energy will be needed to remove the electron, the outer shell electron of sulfur as compared to the outer shell electron of phosphorus. A second reason can be because the orbitals of phosphorus are all half filled, and half filled orbitals are actually very, very stable. So it's very difficult to remove the electrons from half filled orbitals. So that's why. Okay, so that's the second reason, but that's not the main reason. The main reason that you want to, your examiner wants you to write on your marking, on your exams is this one. Okay, it's due to the spin pair repulsion that the outer shell electrons of sulfur are easier to be removed because the the electrons in the p orbital of sulfur are paired. And for this reason, for magnesium and aluminum, it's because the outer shell electron of aluminum is better shielded. Okay, it is in the 3p orbital, whereas the outer shell electron of magnesium is in the 3s orbital. If it is better shielded, then that means it is going to be less tightly attracted to the nucleus, and so lesser energy would be needed to remove it. This was about the ionization energy's general trend and exceptions. Both of them have been revised and covered. Now coming to the electrical conductivity, this is pretty easy, by the way. Only the metals will conduct electricity, of course. So sodium, magnesium, and aluminum are the 3 metals. Aluminum will conduct the greatest. The best conductor would be aluminum, followed by magnesium, and followed by sodium. The reason is because the outer shell electrons in aluminum are 3, right? And I told you that it's the outer shell electrons which are provided to the sea of mobile electrons. So in case of aluminum, there are a greater number of outer shell electrons provided to the sea of delocalized electrons. So I can say that the sea of delocalized electrons of aluminum is more concentrated with electrons. So it is better concentrated with electrons. It is rich in electrons. It is more efficient in electrons, so therefore it is going to conduct electricity most efficiently. Silicon also conducts electricity to some extent because it is a metalloid, so it moderately conducts electricity. The examiner if asks you, so you have to write down moderate, but the remainder elements, which include phosphorus, sulfur, chlorine, and argon, are non-metals, and non-metals do not conduct electricity. Okay, this trend can be asked. Okay, so the answer to this is going to be from sodium to magnesium to aluminum. What's happening? The outer shell electrons are increasing, and so there are more electrons present in the delocalized sea of delocalized electrons in case of aluminum, and so it is going to conduct electricity better than sodium and magnesium. Okay, and this completes this lecture as well. Thank you.